Someone respectful and the entire range.
We're still not. Good fun. Honestly, I'm good. What you need to pen?
They should have reminded me because you second one.
These guys are good. These guys are good. Good job. I don't think you did one. There's no better. I don't think you did one shot. I was just gonna be installed with, I was just gonna go for vanilla. Because I don't chop.
I got.
Oh, $5. $3 for both of them. That's solid, bro. I got a Kroger, get that like $3.50. Great damn, yeah. No, but we got both. He did, well, it's like some feedback, so. Maybe you should, but. We're, yeah, get Sally, whatever. Maybe to Jackson. What? Yeah, back to that. We're really good back. They wrote us two overs.
Actually, brand it was all delivered. No, I'll actually. But I.
So, anybody looking for the weekend? Labor Day weekend, so.
Go out to eat maybe first.
I have no idea.
On the board is a question for relation to complaints. If we have a plane that are intersecting, we want to be able to determine the line of intersection. The intersection between two planes is a straight line. And we need to determine a point on the line and also the direction vector of the line. Direction vector of the line should be the cross product between the two normal vectors. So you find the normal vector to the first plane, that's 2, -3, 1. And the normal vector for the second plane is -1, 2, -1. And the cross product between the two is the vector that's giving the direction of the line. Let's calculate. The reason that a cross product would work because the line of intersection is in both points. So it's so that line is perpendicular to the normal line of the first plane, and it's also perpendicular to the normal line of the second plane. Therefore, it's supposed to be perpendicular to both lines, and therefore, you find the cross product of the two normal vector, you should be able to find the direction vector. So it's all in the perpendicular.
So.
These are the two normal ones, where you can call them 21 and then 2. Wish to find the cross product, let's add one more columns. Initial value. The first. Now we can find the direction vector of the line. The first component is the cross product, and the second and third component, it would be 3 minus 2 is 1. The second component.
Wait. Hold on, wait, that would be. Oh, wait, never mind. I got the form. That would be, okay, I got, never mind.
Finish the calculation of the cross product.
What's so funny?
Let me see, let me turn on the scanner so you can see if the link is alive. Aaron, maybe this is the first time you're attending online. Are you able to open the link? I saw you open it earlier. Oh, because I haven't turned on the scanner. So you won't be able to click that link, but now you should be able to. Finish calculation, the cross product will be the answer. So I lay out the two vector and then getting ready to calculate the cross product. The next component is -1 plus 2, so it should be 1. It's the third component is 2 times 2 minus 3 times 1. Finish calculating this vector. As you can see, the cross product was difficult, but with practice, anything when you practice enough, it gets easier. Oh, let's go back to the page. So if you are not sure if your answer is being recorded yet. Not sure if I've scanned the rules right. I felt like I did scan. The lower corner of the code is inside. Did I get your answer? Did you see your name? It's okay. Alright, so if you have not yet, let's look at the calculation. So I basically identify those number and put it in the vector. And then identify those coefficients and put those coefficients in here. That's vector N1 and 2. The direction vector should be, they should also have those arrow to indicate their vectors. The direction vector of line is the cross product between N1 and N2. N1 cross N2. A cross product is a vector that's perpendicular to both vectors, which kind of makes sense because the line is supposed to be perpendicular to the first normal vector. Second one, how do we calculate cross products? So we multiply and subtract. So 3 times 1 minus 1 times 2, they give you 1 because the first number is 1. The second number is, I moved the 2 and -1 over so that it's easy to multiply and subtract. So multiply and subtract, it's -1 minus -2, which gives us 1. And the last component, we multiply the 2 and 2 minus -1 times -2, that's 3. So 4 minus 3, which also equals 1. Now finish the cross product calculation. So our final answer should be 1, 1, 1. So then if we understand the logic behind it, why would we use a cross product to calculate the distribution of the line? Then the calculation itself is a typical example of cross product calculation. Hope that you were able to finish the calculation. Anyone else? So then for attendance, we reported 22 students today. If you came in late in the day, you can always stay after, ask about the clicker question, so I can complete your attendance. Otherwise, what we have here in the system will be counted as your attendance, like verification for attendance today. Do you have any more question you want to ask before we start talking about chapter 11? We're getting ready for test one. Test one is over all the material in chapter 10. We probably are going to start chapter 11 already, but the test is scheduled for September 4th. That will be next Thursday. So in 1 week, we can have our first test. Hopefully we'll do well. Normally people reported that in Calc 3, the first chapter is one that is easier than the rest of the chapters. This is kind of a bridging chapter. You had a little experience with either linear algebra or a little bit experience in Calc 2. We did a little bit of vectors. So hopefully in 10, everyone will feel more confident once you had practice those questions. Oh, the solution, the practice question and solution for the test one is over here. That was the example of test one. We plan on having a question that I pulled the example of those 8 questions from our homework. That's that was a question. So we definitely need to do cross product, calculate angle, calculate area using the dot product, right? A cross product and then dot product for this one, and then cross product to calculate area. This is calculation of distance from the point to the line, determine equation plane with 3 point, determine the volume of parallelogram. Those are typical questions you saw in the homework. This is determining the equation of a plane through a point at line. And this is find the vector equation for the line of intersections. That's all. So you see, those are very familiar questions. I hope that you can try to focus on those questions in the homework. Now when you get enough practice, the solution is already in here. You can practice over that one, see if you are understanding these materials. These are the solution right below that. It's a solution. Try to practice test 1 and try to finish all your chapter 10 homework. Any questions? Okay, so we started chapter 11 yesterday. Today, let's try to finish what we started. So moving into chapter 11, we're going to study vector value function. And basically, vector value function is when the output of the function is vector. So instead, the function value is not a single number. Instead, that is being the function value. So we don't have a y equal fx. We have x equal this, y equal this, z equal this. So we have multiple formula for the output and put those multiple output into a vector. So you can kind of think of several things as related to t. So giving the t, this is down, this is down, this is down. Kind of like the t is like the labeling. For example, if you look at student record, every student has a student number, but with that student number, you have student name, student gender, student grade. So those are kind of like all of individual question is like a vector that contains all these things. So you can think of vector as a way of organizing multiple information or a table. So vector value function is, think of it as a big table. And so we were going over this in Calc 3, we study vector value function that are 2-dimension or 3-dimension. But you know, the dimension of the output vector could also be 4 or 5-dimension. But in our class, we try to make it more relatable to the physical world. But theoretically, it could be a higher dimension, which requires a higher level of information. Okay, so we were talking about definition of it, giving a t. We have a ft and gt for 2-dimensional function, and we have ft, gt, ht for 3-dimensional vector function. And then that was the example we grabbed together yesterday, and then we also grabbed this one together with the 3-dimensional graph. I had a problem trying to adjust the range, because for a parametric equation for vector value function, T is the parameter, and T is the input value, and it determine the range or the domain for the kind of affected how much we can graph. Okay, we also going over the where you can add to a vector value function, or you can have a vector value function multiplied by a number. And we did this in here. R1 is a straight line, R2 is a circle. If you add R1 and R2, you end up having a spiral here. So the first image showing R1, R2 individually, the line is R1, the circle is R2, we got two vector value function. They could also be the one-dimensional function, like this one could be x1 plus y1, x squared plus y squared equals 1, that's a unit circle. This one could be y equal to 1.5x, but then that you can't add it. So then the vector value function provide this different perspective that being them as vector value function, we can add them, and then we're creating something really different than what could be done using the one-dimensional function. So that is adding the two vector in the first picture, creating the second picture here where the R1 and R2 is being added together. Then this function, if you multiply by 5, you're creating a much larger image. So the smaller one in the middle is what's originally R, and then our vector R times 5 is the bigger one. So that the exercise is illustrating adding vector and multiplying the vector by a number. Have R1, R2, and R, and then 5R all in the same image. This is the one we were finishing up by the end of the class to define a function that represented a cycloid. A cycloid is a graph traced by a point P on a rolling circle, or you can consider that you roll a bike and one point on your bike have a shiny light. As we're biking forward, that point is going the same kind of motion. It happened before, so I saw someone riding a bike like that. So it's kind of funny. All right, so we could imagine the point to be on the. Let me try to. See, we went over this yesterday. I have to switch the sign because I made an error with the angle. So we wish to represent the point P in the picture. Okay, it's being controlled by two vectors. One is this vector, which is the upward vector, and that's called that R1. So the first vector is pointing up. So its x value is the t, and this is where t. So t can go all the way forward. T. The white one is the height, which is the center of the circle. As the biking goes, the center of the bike do not go anywhere. So this vector always have a y value of 1 because the radius of the bike is 1. That's the first vector. Second vector, we imagine what will happen if the bike is moving forward. What happens to that point on the surface? Suppose we start from here. All right, and then as the bike going forward, this point is going this way. So this angle that happened here this way. So if this is angle theta, so we have the angle is going this way, so it's cosine theta. So it's going basically clockwise. The circular motion is the circle is this way. So our angle clockwise. In math, or we look at the point system, if the circle is counterclockwise, it's positive angle. If it's clockwise, it's negative angle. So we actually have cosine negative theta, sine negative theta. So it should be negative sine theta or sine negative theta. Because the circulation is backwards. So the angle goes this way. Here is our theta. It's negative theta. it's a negative theta. This is a clockwise motion. And then we add these two vector to create a summation. So R1 plus R2 is equal to this. So it's equal to T plus cosine theta. And then 1 minus sine theta. Which represent the cyclic motion. And that was here. So we basically combine these two vectors. The first vector is a clockwise rotation. So keep rotating this way because that's what happens when you ride a bike forward. And then the other one is a horizontal motion. That's the center. The CT is representing center of the bike. That was T1. And combining these two together, we go forward and circling as we were going forward. Combining these two, we have that one. And if you graph it on the XY plane, it's a two-dimensional vector, so it's possible to graph it. And we can see how it works. We can graph it today. It's now start to do it. So on the XY plane, we have T plus cosine T for the first component, and then 1 minus sine T for the second. And I will also just try to make it larger to 5. There. So that's the sine formation. Sure. Any question? You can see it produces not exactly at the 0 because you if x equal t equal to 0, cosine t does not equal to 0. So if t equal to 0, 1 cosine t is 1. So that starts from 1. So our x value actually starts from 1. That's why we see that point. And when t equal to 0, that's 1. So the initial point that we started is start from 1, 1. And then it goes down and up, down and up. That's the motion. Any question? So t is not the same as our x value. Our graph is displaying the x value and y value. You have to follow the calculation to see where the x and y is. But it is a cyclic image. Any question? So that's the existing example, and now there are a couple of things we want to be able to mention. Therefore, we can talk about it in the two-dimensional case and three-dimensional case. One thing we would define is called displacement. That is like the name, how much we display from to that. So the calculation for this displacement is subtraction of the two vector. So R is a vector value function. So you have an initial time and terminal time, or initial t value and terminal t value. The parameters start from t0 ended with t1. We want to know from t0 to t1 how much change is happening in terms of motion. So that is subtraction of the vector. And so then essentially we are trying to determine displacement. Think of it from a subtraction of vectors. Suppose that this is R0 and this is R1. Then what happened to R1 minus R0? This one. So then essentially that is a terminal point, that is a terminal point for both vectors. And then you're trying to find how much it's different from this position to that position. So essentially, we don't care how much change is happening. Maybe the point of motion is here, but if you do a displacement, you're doing the calculation from here to here. So the vector, D vector, only counted from this position to that position, how much is in between. That's the displacement. So displacement only care about from the initial point to the terminal point, the absolute distance between the two, or this, the absolute vector start from and then there. We don't care what happened in the middle. Maybe you travel around, maybe when you went to several places and finally arrived there, but we only want to know from here to the top part. That's called the displacement. Some calculation here. This question says we are trying to find and graph the displacement vectors from our t equal to from t equal to -1 to t equal to 1. We want to graph the displacement and also we want to graph the whole function and find the displacement on that interval. Let's see. Follow the definition. Let's try to understand the term, the displacement vector. Right, this is actually two different questions. The first one is graph this whole thing from -1 to +1. Have the you can see it's cosine something, sine something. When you have cosine angle and sine angle, it's very possible. It's on a circle. Okay, but we like sine, cosine, oscillating between -1 and +1, sine oscillating between +1 and -1. So essentially, you're within a circle. But the question is how much of a circle? So we're gonna look at the angle change. So if we're graphing it by hand, and then we can see a circle actually look like this. We have a circle of radius 1. But whether we have the entire circle, that is a question. So let's try to look at the initial point, terminal point. Here we have -1. Now, if t equal to -1, what will happen to the point? We'll have cosine -1 times pi over. So it's cosine -pi over 2. And then sine -pi over 2. Right, which will be x equal to 0. Cosine -pi over 2 is equal to 0. Sine -pi over 2 is -1. So that is this point. That's the initial point. Now we're gonna go from -1 to +1. We halfway in there, we might have to pass 0, being it's a continuous interval. So what is equal to 0? We want to see what we pass by in the past to t equal to 9, t equal to 1. If t equal to 0, that's we have cosine 0, which equal to 1, and we have sine 0, which equal to 0. So that will be the 1, 0 here. So that means we actually go from all the way from 0, -1, back to 1, 0, and then probably back to now if t equal to 1. If t equal to 1, what will happen? T equal to 1, then we have cosine pi over 2. Which is actually equal to 0. The t equal to 1 in the y value is sine pi over 2, which is 1. So that's 0, 1, and I landed here. Right, so that's what happened. So it looks like we don't have the other half of the circle. I mean, I draw the full circle because I knew it was supposed to be part of the circle, but I don't know how much of the circle it actually. So it looks like this representation of cosine pi over 2 times t, sine pi over 2 times t. When t go from -1 to +1, it went the right half of the circle. So that was trying to sketch it by hand. And then the second part, that's the graph. That's the first half of the question. Second half is find the displacement vector on this interval. So on this interval, we did start from -1 to 1, but t equal to -1 to t positive 1. So what happened to the vector? This is the initial point. That was a terminal point to get that vector. Okay, so how do we calculate vector like this? The same way as we did. You would do terminal point minus initial point. So your terminal vector is this. We have the earlier definition. this is our R negative one, which equals this vector. And then over here, this is the R at 1. And so to find the displacement vector, we will be subtracting them. So the displacement D equal to R1 terminal minus initial minus R negative 1. So we subtract these two, and then what will happen is 0 minus 0, which is 0. And then we have 1 minus negative 1, which is 2. So let's represent the displacement vertically by 2 units. So that vector itself indicating that from this point to this point, there's no change in the x coordinate, there's 2 unit change in the y coordinate. And that's what we call the displacement vector. Any questions? And the magnitude of that vector is how far the distance that we travel from initial point to terminal point. That's this example of find vectors, vector value to find this. That was the solution from the book. Pretty much did the same thing. And then let's talk about the next term. It's something that we've done in calculus. Let's calculate average rate of change. When we have y equal to f of x, the average rate of change can be represented by the slope of the function. So it's really y2 minus y1 divided by x2 minus x1. Y2 is supposed to be the terminal point, y1 is supposed to be the initial point, y value. So to find out average rate of change, you have to have the initial point, a terminal point, or x1, y1, x2, y2. That was for the one-dimensional slope of one average rate of change. But now let's talk about how we do it with vectors. Surprisingly, the formula is very similar to the slope calculation. You have terminal vector minus initial vector divided by t1 minus t0. So we think of vector value function, the t is our input value. That's the independent variables change in the denominator. And the dependent variable in the vector value function, dependent variable is the vector. So we actually subtract 2 vectors. When you subtract 2 vectors, the results would also be a vector. So this is the average value or average rate of change calculated as a vector. So here are the examples. Try example. Here it says the same circle, and we want to calculate find the average rate of change of RT on -1 to 1 and on -1 to 5. So these are 2 different intervals. The first interval is t equal to -1. Remember the interval we're talking about t from -1 to equal to 1, and t from -1 to 5. So we want to find out that. Let's see average rate of change. And obviously the longer one. That's the oscillation. The longer one should have a smaller average rate of change. See the calculation. Average rate of change represent average slope or average speed. Yes, in our conditions stabilize. See calculation. Okay, let's try. Let's see if we start with the first one. Okay, so we will notation. There's no special notation, it's just called average rate of change. All right, so I'll just call them R. Average rate of change. So we follow the definition closely. We'll go R1 minus vector value function. These are vectors minus R -1 divided by 1 minus -1. It's 1 minus -1. So the denominator clearly the 2 numerator we have to finish calculating 2 vectors. So numerator. For R1, we plug in 1. I think we've done it before. Plug in 1 for T. We'll somehow return 0. So that was 0. And if R equal 1, then 0, 1. And then, I guess that's really the displacement we had in the previous question. And then negative one is cosine negative pi, that's 0, and then sine negative is negative 1. Right, after we subtract those two vectors in the numerator, we have a vector that is 0 and 2. And this is being divided by a number 2. So our final answer for the average rate of change is vector 0, 1. So first question. The second question, average rate of change, the interval on a longer interval is equal to. So the denominator is 5 minus negative 1, 5 minus negative 1, 6. Numerator is the value of a function at 5. So cosine 5 pi over 2 is still 0. And sine 5 pi over 2, what is it? 4 pi over 2 is still 2 pi, so that's 5 over 2. It's actually 1. Okay, and then cosine negative 5 pi over 2 is also 0. And sine negative 5 pi over 2 would also be negative 1. That would be the same. So you can see because the denominator is smaller, the numerator is still 0, 2. The vector 0, 2. The denominator is 6. Okay, so then the actual rate of change is smaller, at small magnitude. So divide this by 6, we have 0, 1/3. Any question? Okay. That's the answer to this question. Do you have any question from the homework? Let's try go over a few homework from 11.1 to see if we have any surprising question. This question is the last question. There's only 6. I try not to make this section too big. Find the vector value function to represent the curve of intersection of the two parabolas. What is the vector value function? Basically, is a parametric equation, parametric function. So essentially, in this section, if you were trying to find the vector value function, you're constructing a formula for x, y, and z. Now, in this case, x is already given as t. If x equal to t, the line of intersection should fit all 3 equations. There's only 2. Find all 2 equations. This is the curve that's intersecting from the paraboloid and the cylinder. The 2 has the intersection. The intersection is a curve. So if x equal to t, plug into the second equation, x is t, so y equal to 5x squared. Therefore, y equal to 5t squared. So you're using all the information in the question to create a formula for x, formula for y, and formula for z. If the question already gave you a formula for x, then using that x is what you're going to do for the y and z. That's the y value. Now the z value is 5x squared, x equal to t already, because see here, that's t. The x component is t. So as t, so 9t squared plus 5y squared, but y equal to 5t squared. So it's going to be 5y squared. But y is this, y is 5x squared, 5t squared. So we have a 5t squared in the place where the y is. The calculation squared, but the computer probably can do it. So that would be how we enter that one. And any question? So we're using the information that we have a formula for x, and therefore we would already have a formula for y because y equal to 5x squared. Okay, so this is the one that doesn't require a lot of calculation. As long as we kind of see that these formula we're creating have to fit this, have to fit this. These, because of the intersection, so that every curve has to be applied. Now, this number 5, we want to find the parametric equation or actual value function for this curve. The curve is x equal to negative for the square, but this is a curve in the xz plane. So what is the property of the curve that has to be within that plane? In the x plane, the xz plane is in the xz plane, therefore the y value equal to 0. So it looks like this. You can have x value is negative for z squared to t squared. And then let's try to enlarge this. All right, and why do we do that? Because there's a relation between the x and z. So you could see x equal to 4z squared, and then the y is 0, because in the xz plane, the y value has to be 0. Because xz plane is the plane y equals 0. Y equals 0 is a plane, which is representing the xz plane. So xz plane is a plane. That kind of makes sense. Y equal to 0 is actually an equation that represents a plane, and that plane would be x plane. So because it's xz plane, and then here you should be having a z, and that already is the parametric equation for your curve. So you can see when the equation is given, it also provides a way to connect those two variables. It's basically saying between the x and z, they have it's a parabola. It's parabolic relation between x and z. So if you given the z, you can calculate the x is negative for z squared. But then the question says we don't want z to be our parameter. I mean, right now in this vector, the only parameter is z, right? So we have to switch the z to a parameter that we allow it. So that's why we would switch the to a t. That should be the answer for this question. Okay, I hope I didn't overcomplicate things. So sometimes occasionally I see them, they're like, they know it before I explain it, after I explain it, they're like more confused. So if you're still confused, please let me know. This is the question number 4. We want to find a vector value function or a vector parametrization. Or basically is we're trying to find a vector value function for the quarter ellipse from 308 to 048 and centered at 008 in the plane z equal to 8. So one thing for sure, for some reason we are making z equal to 8 since it's in the plane of z equal to 8, and there's no problem that z gotta be 8. And the only problem is we still have to find the x value and the y value. So like 308, 048, and 008, those are indicating that the value is got to be 8, and then the ellipse is in the xy plane. So let's focus on the xy plane to determine the ellipse. And then I think we learned ellipse parametric equation for the ellipse in Calc 2. So in this plane, imagine this is your plane, the equal 8 plane. And then here is your x value, here is your y value. We don't care about the z anymore because we set the 8. So we only care about the x, y. The x is 3, 0. So here we have 3, 0, and 0, negative 4. There we have 0, negative 4. And there's 3, 0. The center is at 0, 0. We're making a circle. Not a circle, an ellipse. So ellipse. So in this ellipse, the x radius, horizontal radius is 3. The radius in the y direction is 4. So the way we can create this ellipse is a circle changing a radius in two directions. So in this case, the x radius 3, so you have x cosine theta. And then the y radius is 4, so we have 4 sine theta. This will be a vector representing the ellipse you see in that image. We'll guarantee that x radius is 3, y radius. Are we okay? Are we okay? Now what we do next is obviously we're gonna put in our formula, but then the thing is in the question, we wish to have the t instead of theta. So we will have 3 cosine t, 4 sin t as our answer. Back to page, the first component will be 3 cosine t. Second component is 4 sin t. It will be on the first part of the. Okay. Polar ellipse from 308 0 negative. The polar ellipse is over here, right? We're not using the full ellipse. That means let me think about it. If it start from 0 negative, it start from 308 to 0 negative 4. Meaning that we want the y value to be negative, so it shouldn't be this part. It should be negative 4 sin theta. I mean, we're not rotating over here, right? If we were having 0 to pi over 2, you would be going through the ellipse in the first quadrant, right? Right? Only if you turn that y value to a negative, no, this is still 0 to pi over 2. But if you make your sign negative 4 sin pi over 2, then it'll become negative 4. I was looking at negative 4 and was like, this is a quarter that the question wanted, but we would have this quarter if that were to be positive. So we have to make it negative. Really watch out for that little, like it's tricky. It could be a trap to follow into the wrong answer. Let's make it negative. That will guarantee that we're in the right quadrant. This is number 4. Any question? Are we okay? I'll leave you to finish the rest. If you still have a lot of difficulty, we can go over them. Yeah, this is the line, equation line. We said equation line already in 10.5. So if it's parallel to the x-axis, it's not, right? This is 0, 5, 1. It's not parallel to the x-axis because x-axis is vector 1, 0, 0. So this has to be false. This is a curve. It's a line segment. So this is a line segment. So this is the x value, and which is identical to this value. So it's really y equals 5. That's the same, right? That's one is the same. So that's x. Y equals 5, x minus 9. It looks like a line, so that should be a line segment. Because the t equal to 0 to 3, so it's not the whole line, only the line between these points and that point. This is the graph. Isn't bad. So y equal to t, so t equal to natural log of t equal to natural log of x. Good. So I guess it should be true. This question are not going to be uniform for every person. So if you see any strange question in number 3, let me know. I'll finish from there, and then we're going to move on to section 2. You can finish the rest of the 11.1 question. If you see anything that's overly difficult, we can try it together. Try 11.2. 11.1 is introducing vector value function, and we're gonna do calculus with it starting section 2. The title is called Calculus and Vector Value Function. So we want to be able to find the derivative for the vector value function. We want to be integrating the vector value function. So we want to try and see if all the concepts that we learned in Calc 1 can also be applied for vector value function. That's the question here. So number one, I start with all this calculus stuff. So how do we do calculus work? We start with limit. Once we understand the notion of limit, we have continuity. If the function is continuous, we want to look at the tendency by studying the derivative. Derivative is a slope of the curve, therefore representing a rate of a change. And then once we have the derivative, the opposite of the derivative will be integration. So limit is like the initial part of the calculus study. Here we're defining the epsilon delta definition for the limit of a vector value function. Suppose RT is a vector value function, and then let's define the limit of RT when T approaches the number C. When T approaches number C, we see the limit of RT is L, vector L, if that means that for any epsilon bigger than 0, we can find the delta 0 such that whenever T and C is closer, T is closer to C by less than delta, that's the indication that T and C is really close. And we have our T and L, it is also very close. This closeness is measured by the magnitude of the vector, which is less than epsilon. So when the magnitude is small, smaller than epsilon, we're saying the limit of the vector is L vector. So that is our official definition. We follow the epsilon delta definition that we had in Calc 1. But now the underneath is a hidden notion that all those notation, the RT minus LT is not subtraction number. These are subtraction vectors. Therefore, it's not absolute value that we measure, it's magnitude that we measured in the last formula. All right, so that was the definition for limit. And then here, all the limit rules still apply. For example, if you want to find the limit of a vector, well, the first one is applying to the vector value function. Limit of a vector equal to limit of individual component. So finding limit, if you can find limit of function, you're able to find limit of the vector. Second one is saying this same thing applies to the three-dimensional vector. So limit of three-dimensional vector really is a vector of the individual limit of component. That's so we can actually turn the calculation limit of vector into a calculation limit of function for each component. Okay, so for example, let's say we want to find a limit of RT when T is approaching 0. This function, we got three functions to worry about. So we want to find limit of the sine T over T when T approaching 0. That would be 1. We want to find limit of T squared minus 3T plus 3 when T approaching 0. That will be that will be 3. The last one is when T approaching 0, cosine 0 equal to 1. So the limit of these vectors when T approaching 0 is 1, 3, 1. Any question? So you can think of RT as a three-dimensional curve, all right? And then that means saying it's that T approaching 0. So 0 is representing one location on the curve. So having a limit means that you can approach that point from both directions, right? The left direction of the 0 and the right direction of the positive T and negative T. When T is getting closer to 0, the curve is getting to the point 1, 3, 1. Now that we have limit defined, let's define continuity. Like I said, if you can approach it from both sides of the equation, then the curve is continuous at that point. If RT is a vector value function, and we see that RT is continuous at a point C, if the limit of the function, if limit of the vector RT when T approaches C equal to the value of the vector at C. So basically, limit of the function equal to the function value. That's considered continuous at a point. And then next is continuity of the entire function. The entire vector value function is continuous on the entire interval of I, whenever continuous at every point in I, every point C in I. That's pretty much the vector value version of the same definition in calculus. Question. So we define continuity using the limit. That's why limit definition always comes before the continuity definition. Okay, this is trying to connect what we have in calculus 1. We want to start over with a determination of continuity. So according to what we have, if you want to study a vector value function, you can study individual vector. That means if every component, well, that's not. This is about a vector defined an open interval. Right. So if every component is a continuous function, then the vector value function itself is continuous. So the continuity can be studied individually at the component level. So then all the continuous function property that we had in part one still apply here, which have to do with three different ones. If it's three dimensions. Okay, so here we determine if the function is continuous at point t equal to 0 and t equal to 1. We start with the t equal to 1. If t equal to 1, you see the first function sine t over sine 1 over 1. That is well defined, that's continuous. At t equal to 1, the second function is polynomial. Polynomial is well defined for all functions that's always continuous on the entire number line. Cosine t is continuous on the entire number line, therefore continuous for the first one. So we should not have any problem with the second and third component because those are the functions that are continuous on all real. So polynomial is continuous on the entire number line. Cosine function is continuous on the entire number line. The only problem is the first one, right? The first one has a division. Division by 0 is undefined, therefore it's discontinuous. So the first function is not continuous when t equal to 0. Any question? Right, with all that, our conclusion will be that vector R is continuous at t equal to 1, but it's not continuous at t equal to 0 because they fail as the first component. Any question? So the study of continuity becoming study of continuity for each component that we made in the conclusion we had earlier now still works. Okay, now let's move on to derivative. Now that we have continuity, because the function is continuous, we are able to study the closeness of the curve. That is, what exactly is a derivative? Is the direction of the curve. And we have talked about derivative before. Derivative is the slope of the tangent line or direction of the curve. Now, if you have a smooth curve, you will have a direction, you will have derivative. Smooth curve always have derivative being at vector value or regular value. But if your curve have sharp corner, or if your curve have discontinuity, then this direction does not go this direction. Okay? So that's why we design highway, they're always smooth, they always have continuity and derivative. But then we never design any road that way. We always kind of smooth it out a little because you want to make sure that derivative exists. And also, if there's any break, we have a little bit of problem. And then you got no direction there. We will be stuck at the discontinuity or any sharp corner in the curve. Now, let's go by the original definition for derivative. Definition for the derivative is the quotient, the difference quotient. According to the definition, I don't know if you remember, we will find the point given, which is C, and you go forward and backward from point C. For example, C plus H. So that's a small change from C, and you calculate the difference between the output value divided by the difference of the input value. The input be C plus H minus C, which is H. That's called, so division. Division is called a quotient in mathematics. So this is a quotient of the differences, which is called quotient, difference quotient. So the limit of difference quotient is being defined as a derivative. So the quotient represents a slope. And when you find the limit of the slope, you're determining the instantaneous slope or instantaneous rate of change. That's our derivative. Derivative represents the direction of the curve. Okay. Any question? I think the two are the same. Right, I think the two are the same definition. Definition of this, the definition for the derivative at a given point. This is definition of the derivative of the entire thing, the entire function. question. It's not too far from the derivative definition in Calc 1, right? It's actually the same. In Calc 1, we have f of c plus h minus f of c divided by h, and h approaching 0. Now instead of f, we have r vector r. We switch the function value as a vector, and the vector is actually a vector value function, so still it's a function. Okay. And then again, move on to calculation. Do we have to relearn the linear definition of derivative? No, because we have already studied derivative calculation for individual function. So derivative calculation can be worked out component by component. So if you want to calculate derivative of the vector value function, all you have to do is find the derivative of the first component, find the derivative of the second component, or finding the derivative of the third component. All those derivative is the derivative of our vector. Any question? The derivative of vector value function. Okay, so this is a question. Try to sketch or calculate them and see if it makes sense as far as representing the direction of the curve. We would have calculated and graph the original function and graph the derivative. And also the second question is to calculate r prime 1 and sketch the direction. Let's see. Let's see if I can do it faster with the grapher, the computer graphic. How do we? The first one is to sketch RT, which is that one. It's degree 2 function, so I can almost imagine we got a parabola at our hand, x equal to t squared, y equal to t. You can graph it and see how it looks like. So if you graph the original function, it goes t squared and then t. And let's try to make it larger to see the full pictures. So it's a parabola opening to the positive x direction. And we can also tell it from combining them. If you try to combine them, because y equal to t, you can bring the t in here. Then you have x equal to y squared. Okay. So x equal to y squared. We mentioned the relation between the two variables. If one variable is squared, the other one is not. So degree 1 variable and degree 2 variables added together. That's a parabolic relation. Except this parabolic relation, the y is the input, x is the output. So open to the positive x direction. That's why the parabola looks like this. So if you write this parametric equation into its xy form, you kind of understand more of the relation that we got parabola. That was 90 degree, and then there's usual parabola. The usual parabola is y equal to x squared. So now we have x equal to y squared, which turn 90 degree. Open the parabola open to the x direction. Okay, so that was the graphing part. You can also graph it by hand. I did it with a computer graph. If you want to graph it by hand, you might want to, like we did here, I make t equal to -5 to +5. You have to make a table. T equal to 3, 2, 1, 0, -1, -3. With every t, you calculate their x value and y values, and you graph those points, and you connect those points to get a picture. Are we okay? You understand how to graph it? You feel like you can graph it yourself? Okay, so leave that. Leave that ability. If I have to graph it by hand, it's more time consuming, but that's the graph for RT. Second, we were to graph the R prime. Another thing we need to graph R prime, we graph on the same plane, but we first have to calculate it, right, in order to draw this. We got this R prime of t, which equal to a vector. We find the derivative of t squared is 2t, derivative equal to 1, right? And now that we have those components, we can now graph it. So we would have 2t and then 1. So how does it look like? Let's try to make it -5 to -x. Let's follow, right? It's a horizontal line. So we're saying when t equal to, it has been horizontal. What does it mean? So that means the whole thing has been in the x direction. So has been, it depends on the t, right? If t is positive, it went all the way up. So this is t equal to -5 below there, and then that's t equal to 0, and that's t equal to positive. For the positive one, you can see the x is getting up and up. So that when t is positive, the 2t is positive. So the x value gets bigger. But it also says the slope in the y direction is 1. So what we observe is the y value has been 1, 1, 1, 1, 1. And it's been just keep increasing in a steady speed. Are we okay? So x value has been going way to the increase way fast when t equal to positive value, but the y value is still increasing with the y as the x is increasing much faster than the y. The y is constant as far as speed. Are we okay? Okay, so it kind of represented the rate of change in two separate ways, the x direction and the y direction. And that was the graph. And then the second part of the question is to calculate. We were to calculate r prime 1 and also sketch the r prime 1. And also sketch r prime r1. Okay, so r prime 1. Here we have r prime. So t equal to 1 is 2 times 1. That's 2, and then so we got 1. That's this function, and then the r1 vector r1 is the r. That's 1, and then so it's too hard to graph them on the same picture. Okay, so for 1, 1, you identify the point 1, 1. There's 1, so you graph it like this. Okay. And then we also want to graph this r prime 1 is this. R prime 1 is 2, 1, so you get 2, and there's 1, so you graph this vector. All these are supposed to be vectors. There. Any question? So that's the second picture. I think that finished most of these questions. That was given in the textbook. This is the first picture. We graphed the parabola, and that was the derivative of the vector. Over here, those are the two. We were supposed to start from the initial point. That's r prime 1. And where was the r1? That's the from one from the initial point. R1 was the r prime 1 is 2, 1, 2, 1. I don't see the vector r1. So we're not drawing the r1. We're drawing r prime at each point r1. Let's see. At least I understand. Any question there? Okay. So basically, the second question is actually drawing the r prime 1 twice. One is from the origin. One is from the point 1, 1. You draw the r prime 1 again. So what we intend to illustrate is that if r prime 1 indicated the direction of the curve at the point r1. Okay. At the point 1, 1, it seems to be tangent to the curve. So then the second, the tangent arrow is more the intention of the different. So we should draw the vector instead of drawing the vector from the origin like this. And that was the derivative. And yes, there's quite a few sketching questions. I'll try to move on from there. What we're calculating represent derivative. A derivative is direction of the curve. Now that we have the derivative, that we use the derivative of the vector value function, we're able to draw the tangent line. So here we're gonna try to devise a formula for how to draw the tangent line. We have already have a way to represent lines. In 10.5, we have formula for the line. Formula for the line will be a point plus t times the direction vector. Now, according to what we have in calculus, the direction vector for the tangent line should be the derivative vector. So now we have the derivative. If you have a vector value function, the derivative would be every single component you gotta find its derivative. Now you have the r prime c or r prime t is the derivative vector, and the derivative vector is the direction vector of your tangent line. So being able to find the derivative of your function allows you to determine your tangent line. So how do we write our tangent line? Tangent line is also equation of lines, so you need point, and also you need the direction vector. So what was the point? The point should follow, it's a point on the curve, so the point should follow the original vector value function. So all you have to know is the tangent point. In a parametric form, at the tangent point, the most important thing is to find the value of the parameter. In this case, it's t equal to c. So the equation of the tangent line at point t equal to c would be at the bottom formula. That's rc plus t times r prime c. R prime c is the direction vector, therefore that's a derivative vector. And then RC is a function value vector, because we got vector value function, and that's our formula for the tangent line equation. So then the vector valued tangent line equation is different than what we have in the tangent line equation in calculus. Any question? So you can think of the tangent line equation that we had in calculus as one-dimensional tangent line, but this is multivariable tangent line. Okay, so let's look at an example. Here we have a curve t squared t cubed. It's pretty much a cube curve, a cube curve. This curve is being defined from t to the -5 to t to 1.5. We want to find the vector equation of line tangent to the graph at t equal to -1. So that is the example of tangent line equation, calculating the tangent line equation. I mean, as usual, a tangent line is still a line, so we need to find a point and the direction vector as usual. So now that it's just that the direction vector has to follow the derivative calculation. So that's the point of tangency that we need to calculate. So you're going to use the t equal to -1 to identify the point. So we can calculate r -1, plug in -1. For t, we have -1 and -1 squared, which is +1, and -1 cubed is still negative. So that's a point for the line. Okay, and now we're gonna work on the direction of the line. So direction vector d actually equal to r prime at -1. The derivative of the vector value function allows us to determine the direction of the curve. In that case, I got no derivative. Finish. So r prime of t is equal to derivative t equal 1, derivative t squared is 2t, derivative t cubed is 3t squared. So having the derivative formula should be the derivative at -1. So the vector goes 1 and -1 onto -2. 3 times -1 squared is 3. That's the direction vector. So yeah, our direction vector, we also have our so all vectors that should be labeled as vectors. Okay, so now the equation of the line would be LT is equal to the point, which is -1 at 1, and then -1 plus t times 1 negative 2, and that's the equation. That will be the vector equation of the line. Any question? So all we need to know that's new in the section will be the direction of the tangent line is the derivative vector. So that would be good. That's what we have. That might be different than before, but they kind of combine what we were learning in the last chapter. That is equation of the line now be repeated, applied again, which allows you to calculate for any curve we can determine its tangent line now. Those are the calculations. And it even produces the picture. The blue curve is the curve itself, and that was the line that we're showing. This is a point negative 1, 1, 1. That was the point of tangency right there. And we draw a line at the point of tangency with the given direction. Okay, how to determine smooth curve? Whenever you have well-defined derivative, then you got your smooth curve. If the derivative does not exist, okay, let's see. RT to be differentiable. That means RT has derivative on the entire interval. RT is smooth on I if R prime T is not 0. So that means if the derivative equals 0, it's not a 0 vector at C. So I think we would possibly have a sharp corner whenever the curve have a 0 vector for students. That's kind of like the case when you have, for example, x equal to t squared and y equal to t cubed. It would be a curve, and then you can see when t equal to 0, x prime equals to t, y prime equals to 3t squared. Okay, now it will be smooth whenever both of them are not 0. If the t equal to 0, what will happen? Then x prime will be 0, y prime will be 0. If both of them 0, we have a problem defining it. It will be a sharp corner at t equal to 0. You can see that from the picture. Just trying to say why this will make sense when the vector, derivative vector equal to 0 vector. What will happen? We have a curve of t equals t squared for x and t cubed for the y. And then let's see, let's make the entire, it's -5 to +5. See, it has a sharp corner right in the middle. That's when the t equals 0. If you only have, so the whole curve is all smooth from 0 to 5 or -5 to 0, except at 0, it has a sharp corner. So it would have well-defined tangent line or it's differentiable anywhere except right there when t equal to 0. That's the point. If t equal to 0, the derivative is 2t and 3t squared. The derivative vector is 0, 0. Or in the three-dimensional, you have 0, 0, 0. That means the derivative does not exist, or slope does not exist. And that will we would have problem. We would not be able to define tangent line because you see, your given point in this case is 0, 0, 0, 0, 0 plus t times 0, 0, right? You really don't have a tangent line there. That would be the curve will not be smooth when the derivative is a 0 vector. And that will be it for today. We'll try to finish the 11.1 homework if you have time. In the meantime, try to finish chapter 10 because we have this coming up next Thursday. Let me know if you have any questions. Try to practice question. See you next week. Next Tuesday, right? We have no class on Monday because we're Labor Day. Monday is Labor Day.
I'll scan for my end insertion.
You can thank you. Thank you. What were you on?